Hello, the work I'm presenting deals with adversarial attacks in audio machine learning systems. Adversarial attacks add an imperceptible perturbation to the speech waveform, which alters the output of the speech and speaker recognition systems. These systems may be in sensitive applications like personal authentication to access bank accounts or buying things online. So these attacks pose a major threat to security. The goals of this research are to detect when an audio system is under attack, and also infer the characteristics of the tool chains used to generate the attacks, for example, the attack algorithm. Also, to detect unknown tool chains. The approach we follow is deep metric learning. So we want to learn attack signatures or attack embeddings that encode the properties of the tool chains behind the attacks. And for this, we use S-vector-like neural architectures. In this work, we want to infer three properties of the attack tool chains. First, the threat model of the attack. The threat model is the set of allowed perturbations that we can make to a signal to create the adversarial sample. This is usually defined by a distance matrix, and we consider four types of threat models: L0, L1, L2, and L-infinite threat models. Second, we want to know the attack algorithm. This is the algorithm that is used to compute the optimal perturbation. And there are many algorithms in the literature: Fine-Grained method, iterative FGSM, projected gradient descent, Carlini-Wagner, etc. And finally, we want to know the strength of the perturbation. For example, to measure the strength, we can compute the signal-to-noise ratio between the power of the benign signal versus the power of the added adversarial perturbation. Here we can see some TSNE plots of the learned embedding. In the first one, we had a different color for each pair of algorithm and threat model. In the second one, we have a color for each threat model. And in the third one, we have a different color for each signal-to-noise ratio. We can see that in general, there is good separation between the classes. The benign signals in blue are well separated from the attack signals. Also here, we have a smooth transitions between high SNR attacks and low SNR attacks. Here, we train the embedding extractor on both LED2 speaker identification attacks and test on both LED2 speaker identification attacks with 90% algorithm classification accuracy. Also, both LED2 speaker verification attacks with 74% accuracy and libre speech recognition attacks with 61% accuracy. And finally, we experimented detecting attacks algorithm not included in the training with 90% equal error rate. Check out our paper if you want to know more.